Welcome, my dear learners, for this course on mechanical vibrations. In this module 2, we are discussing on forced vibration and vibration measuring instruments. So far, we have discussed theoretical aspects of part A, that is forced vibration. Before moving ahead to discuss vibration measuring instruments, let us solve numerical problems on forced vibration first. So in today's lecture, we are beginning the discussion on numerical problems on forced vibration. Before moving ahead for our problem number 1, let me recollect the formulas which we have derived in the forced vibration system analysis, what we have done so far. So moving ahead for recollecting the expressions what we have derived in forced vibration analysis. Coming for formulas. So in the first lecture, we have discussed the forced vibration of a system subjected for harmonic excitation. So in harmonic excitation, we have derived expressions for, in harmonic excitation, we have derived expressions for magnification factor or amplitude ratio, which is given by A by static deflection XS, which is equal to 1 divided by square root of 1 minus omega by omega n whole square plus 2 zeta omega by omega n whole square. And also we know that natural frequency omega n is given by what? Square root of k by m. Omega n is given by square root of k by m. Zeta is given by c by cc, where cc is 2 root mk. This is for linear vibrations. For torsional vibrations, you should replace mass by mass moment of inertia, force by torque, and stiffness by torsional stiffness. That you people already know. Next, apart from this, we have derived expressions for resonant amplitude. Under harmonic excitation, we have derived expressions for resonant amplitude, that is A max is equal to XS by 2 zeta, correct? Resonant amplitude, that is at resonance the amplitude of vibration is maximum. So for this to be satisfied, omega must be equal to omega n. This you people already know. And next, we also determined the expression for omega max. Omega max is equal to omega n into square root of 1 minus 2 zeta square. Square root of 1 minus 2 zeta square. And omega damped natural frequency is given by what? Omega n into root of 1 minus zeta square, that's all. Omega n into root of 1 minus zeta square. So these are the expressions we have discussed, and also we have discussed expression for phase angle, correct? The phase difference between the amplitude of vibration and exciting force. The phase difference between the amplitude of vibration and exciting force is given by tan phi, which is equal to 2 zeta omega by omega n divided by 1 minus omega by omega n whole square. So this is the phase difference between the amplitude of vibration and exciting force. So these are the things we have discussed in our lecture 1, correct? And in lecture 2, moving ahead for lecture 2, we have discussed rotating and reciprocating unbalance, correct? Rotating and reciprocating unbalance. In rotating and reciprocating unbalance, we have derived expression for A by XS, where XS is given by m naught E by m, where XS is given by m naught E by m. So m is mass of the machine including the unbalanced mass, whereas m naught is the mass of unbalanced mass, E is the eccentricity, This is equal to what? This is equal to omega by omega n whole square divided by square root of 1 minus omega by omega n whole square plus 2 zeta omega by omega n whole square. Correct? Now the phase difference between the amplitude of vibration and the exciting force is nothing but tan phi, which is already known for us. Next, moving ahead in lecture 3, what we discussed in lecture 3, we have discussed about support motions, which is important for design of seismic devices, that is vibration measuring instruments. Now under support motion we have discussed again two types. One is absolute motion, the amplitude ratio of absolute motion, that is A by B, where A is the absolute displacement of vibrating body, B is the absolute displacement of the support, is given by root of 1 plus 2 zeta omega by omega n whole square divided by square root of 1 minus omega by omega n whole square plus 2 zeta omega by omega n whole square. Clear? Now the phase difference between the displacement of the vibrating body and the exciting force is tan phi, whereas the phase lag between these two, is given by phi minus alpha. Correct? The phase lag between displacement of vibrating body, displacement and exciting force, is phi, force, that is tan phi, which is equal to 2 zeta omega by omega n divided by 1 minus omega by omega n whole square, whereas the phase lag between the vibrating body and the support is given by tan alpha. Correct? The phase lag between A and B. What do you mean by A and B? A is the absolute displacement of the vibrating body, B is the absolute displacement of support. This is given by tan alpha. Tan alpha is equal to what? Tan alpha is equal to 2 zeta omega by omega n. Same thing holds good for transmissibility ratio. Correct? Same thing holds good for transmissibility ratio, that is phase lag between transmitted force and exciting force is tan alpha. Correct? Before moving for that, let me complete for relative motion also. For relative motion, we have Z by B, where Z is the relative displacement of vibrating body and B is the absolute displacement of the support. Z by B is equal to omega by omega n whole square divided by root of 1 minus omega by omega n whole square plus 2 zeta omega by omega n whole square. Clear? And let me write transmissibility of force here itself. So this is equal to what? This is also equal to Ft by F. Force transmitted to the foundation to the exciting force is a transmissibility ratio, which is nothing but amplitude ratio of absolute motion. And this is the phase lag between the displacement and the exciting force. Phase lag between ft and f is alpha minus phi, correct? ft and f is phi minus alpha, sorry, phi minus alpha. It is phi minus alpha. Phase lag between A and B are force transmitted and exciting force. F is nothing but phi minus alpha. Phi minus alpha, where alpha is already known for us. Alpha is what? Tan inverse of 2 zeta omega by omega n. Correct? Because if you recollect the sketch, it is like this. If you recollect the sketch, we have the sketch like this. Let me write here. So it will be like this. We have this is Ka, perpendicular to which we have damping force C omega A, and we have inertia force at an angle of 180 degree to spring force. This is inertia force, and we have force applied force F. Applied force F. Let me use different chalk to show it properly. Let us have the reference like this. So if I have the reference like this, so this is force F, correct? Now from here to here, it is force transmitted to the foundation, because force transmitted to the foundation is spring force and damping force only, which we have clearly discussed in our previous lecture. In our previous lecture we have discussed critical speed of shaft. Previous to previous lecture we have discussed transmissibility ratio, and this is force transmitted to the foundation, Ft, correct? This is what force transmitted to the foundation, Ft, right? Now if I mark the angles between these two, we have phase angle phi, that we know. This angle is phi. Now this angle is alpha. This angle is alpha. This angle I am speaking about. This angle is alpha. This angle is alpha. Now what is the angle between F and Ft? Angle between F and Ft is phi minus alpha. Phi minus alpha. So therefore the theoretical background should be very strong in order to solve problems on force vibration. And this is inertia force, which is m omega square A. M omega square A is the inertia force. So this is about transmissibility. This is about transmissibility. Transmissibility is same as absolute motion. Now moving ahead, we have discussed in our previous lecture, we have discussed critical speed of shaft. Critical speed of shaft. So coming for critical speed of shaft, under that we have two cases. One is without damping. Case 1 is without damping. For without damping, we have x by E, deflection by eccentricity is given by 1 divided by 1 minus omega by omega n whole square, where omega is the excitation frequency, omega n is the natural frequency. Here omega n can also be calculated with the help of root g by delta, where delta is static deflection. Omega n is given by root of g by delta, where delta is static deflection, g is acceleration due to gravity, 9.81 meter per second square. And also we have discussed critical speed of shaft for with damping. Considering damping, with damping the ratio x by e is given by omega n whole square divided by square root of 1 minus omega n whole square plus 2 zeta omega n whole square. Under the root. Let me take inverse since I don't have space. Let me write it properly. That is, we have omega n whole square into square root of 1 minus omega n whole square plus 2 zeta omega n whole square inverse minus 1 to the power of minus 1, because this should come to denominator. So these are the formulas which we have discussed so far. So here I didn't write excess, right? Excess is given by what? Excess is given by f naught by k. Excess is given by f naught by k. The transmissibility of forces is same as absolute motion, so therefore I have clubbed here itself in order to utilize the space properly. That's it, right? So these are the things we have discussed in our previous 5 lectures. Lecture 1, lecture 2, lecture 3, lecture 4 and lecture 5. Now moving ahead, let us solve our problem number 1 by recollecting these formulas. I am discussing the solution to the question bank which I have attached to the link given in the description. Kindly click on the link given in the description below this video to get access to the question bank. For that question bank, I will be discussing the solution in this lecture series. Now the problem number 1 states that a vibrating system having mass 1 kg is suspended by a spring of stiffness 1000 Newton per meter and it is put to harmonic excitation of 10 newtons. Assuming viscous damping, determine A. resonant frequency, B. phase angle at resonance, C. amplitude at resonance, D. the frequency corresponding to peak amplitude, and E. damped frequency. Take C is equal to 40 Newton second per meter. If I list out the data given for problem number 1, a vibrating system having a mass m of 1 kg is suspended by a spring of stiffness K of 1000 Newton per meter and is put to harmonic excitation under a force F naught of 10 newtons. Assuming viscous damping, determine A. the resonant frequency, that is omega, which is equal to omega n at resonance. B. the phase angle at resonance, 5 at resonance. Then he has asked C. the amplitude at resonance, that is A max, amplitude at resonance. D. the frequency corresponding to peak amplitude, that is omega max. and E, find damped frequency, omega damped. Take C, he has given the value of C. C can be taken as 40 Newton second per meter. 40 Newton second per meter is the value of C. Let us solve this problem. If I move ahead for solution, of our problem number 1, we know mass, we know stiffness. So therefore I can find natural frequency omega n, which is equal to root of k by m, which is equal to square root of 1 divided by 1000. Sorry, root of 1000 by 1, right? K by m. How much? 31.62. 31.62 radians per second. Now, very first one, what he has asked is the resonant frequency at resonance. At resonance, omega is equal to omega n, which is equal to 31.62 radians per second. Therefore, resonant frequency will become omega n by 2 pi. So this answer divided by 2 pi, which is nothing but 5.03 hertz. 5.03 hertz. Next, moving for second one, B, phase angle at resonance. B, phase angle at resonance. We know that phase angle tan phi is given by 2 zeta omega by omega n divided by 1 minus omega by omega n whole square. At resonance, omega is equal to omega n. So if I put omega is equal to omega n, this will become 1. 1 minus 1 is 0. So therefore anything divided by 0 is infinity. So tan inverse of infinity is how much? Tan inverse of infinity will be 90 degrees. Correct? So therefore phi is equal to 90 degrees. Hope you understood. At resonance, omega is equal to omega n. So if I substitute omega is equal to omega n, this will become 1. 1 minus 1 is 0. Anything divided by 0 is infinity. Phi is equal to tan inverse of infinity. So tan 90 is infinity. Hence phi is 90 degrees. Next, A max, C, maximum amplitude. A max is given by what? Xs by 2 zeta. Now we don't know what is the value of zeta and xs. Correct? Xs is given by f0 by k and zeta is given by c by cc. Zeta is given by c by cc. Again cc is given by 2 root mk. C by 2 root mk. So hence zeta will be how much? C is known, 40 divided by 2 into root of m into k, 1 into 1000. So zeta is 0.632. 0.632, whereas f0 by k is how much? f0 is 10, k is 1000. It is 0.01. 0.01 meters. Now substitute here, we will get A max. How much is A max? A max is equal to 0.01 divided by 2 times 0.632, which is 7.9 into 10 to the power of minus 3. 7.91 into 10 to the power of minus 3 meters. Done. Now moving for D is omega max. So we know that omega max is given by omega n into root of 1 minus 2 zeta square. 1 minus 2 zeta square. So therefore omega n is 31.62 into root of 1 minus 2 into zeta square, 0.632 square, which is 14.18. 14.18 radians per second. And finally we have E, that is omega damped. Omega damped is nothing but omega n into root of 1 minus zeta square. Omega damped is given by omega n into root of 1 minus zeta square. How much you will get? You remove 2. You remove this 2. If I remove that 2, I will get the answer as 24.5. 24.5 radians per second. 24.5 radians per second. Done. So this completes the solution for problem number 1. Let us move for problem number 2. The problem number 2 states that a flywheel of mass moment of inertia 0.1 kg meter square is suspended from the thin wire of stiffness 1.2 Newton meter per radian. A periodic torque having a maximum value of 0.6 Newton meter at a frequency of 4 radians per second is impressed upon the flywheel. A viscous dashpot applies damping couple of 0.8 Newton meter at a angular velocity of 2 radians per second. Determine first one, maximum angular displacement, maximum couple applied to the dashpot, critical damping coefficient, angle by which the angular displacement lags the torque. So if I list out the data given for problem number 2, a flywheel has a mass moment of inertia I is equal to 0.1 kg meter square, is suspended by thin wire of stiffness. It is torsional problem, hence KT is 1.2 torque per deflection Newton meter per radian. A periodic torque having a maximum value of 0.6 Newton meter, that is torque applied is 0.6 Newton meter at a frequency of omega is 4 radians per second, is impressed upon the flywheel. A viscous dashpot applies damping couple of 0.8 Newton meter at an angular velocity of 2 radians per second. So we have a dashpot. So the dashpot details is dashpot applies a damping couple of 0.8 Newton meter at an angular velocity, that is theta dot, at an angular velocity of 2 radians per second. 2 radians per second. So here this must be T naught, that is the amplitude of torque. Determine maximum angular displacement. First one theta max. Second one maximum couple applied to the dashpot, that is damping force. Critical damping coefficient CC, and fourth one angle by which angular displacement lags the torque, phi. Now let us solve this problem If I move ahead for solution of problem number 2, we know mass moment of inertia and we know torsional stiffness, so therefore I can find natural frequency omega n. Omega n is equal to root of k by m, so k should be replaced by kt, mass should be replaced by mass moment of inertia. Hence I'll get the natural frequency as 1.2 divided by 0.1, which is nothing but 3.464 radians per second. 3.464 radians per second is the natural frequency, whereas the excitation frequency is 4 radians per second. Now we has given the torque applied, so this is F. Instead of F naught, I should take T naught because we are using torsional analysis. Now coming for dashpot, we have damping torque per unit velocity. So damping coefficient is defined as damping force per unit velocity. Force should be replaced by torque and x dot should be replaced by theta dot. So therefore C is equal to, what is the formula for C? C is F by x dot. In torsional systems it is T by theta dot. Hence he has given the value of C as 0.8 divided by 2. How much is C? C is 0.8 by 2. It is turning out to be 0.4. 0.4, it is damping torque Newton meter per radians per second. So Newton meter second per radian is the unit I am going to get. What else we can calculate? That's all right. Now coming for theta max. Theta max is the maximum displacement. We know that maximum displacement is A max. Here it is theta max. So therefore theta max, A max is xs by 2 zeta. Theta max is nothing but, it is also xs by 2 zeta. So xs is given by F naught by k. F should be replaced by torque and k should be replaced by kt for torsion problems, divided by 2 zeta. Clear? Now what is the value of zeta? Zeta is C by cc. Zeta is C by cc. C is known 0.4. cc is 2 root mk. M should be replaced by I. K should be replaced by kt, torsional stiffness. Now if I substitute and solve, I will get the damping coefficient zeta as 0.4 divided by 2 times square root of mass moment of inertia is 0.1 into torsional stiffness is 1.2. So damping coefficient is 0.577. 0.577. So if I substitute these values, I will get theta max in radians as, we know that damping torque T naught, we know the force applied F naught should be replaced by T naught. Here the torque applied is given as 0.6. So substitute T naught as 0.6. kt is also known. Zeta we calculated. Hence how much I will get? T naught is 0.6 divided by kt is 1.2 into 2 into zeta is 0.577, which is turning out to be 0.433 radians. Moving for the second one, that is damping force or couple, because here we are discussing in torsional systems. So damping couple is already known for us. Damping force is C omega A. Damping couple will be C omega theta. C omega theta. Now what is the value of theta? Theta is also unknown. This is theta max, not theta. I want theta. So theta is nothing but amplitude, right? So use this equation, replace A by theta, amplitude of vibration, that is theta by A. What I mean to say is that theta is nothing but amplitude of vibration. So theta by xs, xs is f naught by k, here it is k naught by kt. So a by xs, theta by xs should be equal to 1 divided by, so I'll multiply this here so that I can directly write the answer. So I'll multiply that here, this will be equal to t naught by kt, xs divided by root of 1 minus omega by omega n whole square plus 2 zeta omega by omega n whole square. Correct? So I have used this equation, a by xs, where a is the amplitude of vibration, here also theta is the amplitude of torsional vibration, theta. So find the value of theta. So if I substitute and solve, what I am going to get for theta? T naught by k. T naught is 0.6 divided by kt. Kt is 1.2 divided by square root of 1 minus, again brackets, omega by omega n. Omega is 4, omega n is 3.464, square, again square, plus 2 into zeta. Zeta is 0.577 into omega by omega n. Omega is 4, omega n is 3.464 whole square. So if I solve, I'll get theta value as 0.364 radians. I'll get the value of theta as 0.364 radians. The value of theta is turning out to be 0.364 radians. Now we know all the values, hence damping couple will be C omega theta. C is how much? 0.4. Omega is 4 radians per second. Theta is 0.364. So I'll get the answer as 0.582. 0.582 Newton meter. Done. Now move for third one, CC. Critical damping coefficient. CC is 2m omega n, right? So I can write it as 2i omega n, or I can write it as 2 root mk. M should be replaced by I, k should be replaced by kt. 2 root I kt, that is also correct. Or I will use 2m omega n, that is 2i omega n for torsion systems. What I will get? 2 into I is 0.1 into omega n is 3.464, 0.6928, 0.6928 is the CC. Unit of CC is same as C, that is Newton meter second per radian. Newton meter second per radian. And at last we have fourth one, that is phi. Phi is equal to what? Tan phi. We have the expression for tan phi. Use this one, find the value of phi. So phi will be equal to shift tan inverse of 2 zeta. 2 into, how much is zeta? Zeta is 0.577, 2 zeta omega by omega n. Omega is 4, omega n is 3.464 divided by 1 minus omega by omega n square. Omega is 4, omega n is 3.464 square. If I solve, I'll get phi as minus 75.95, minus 75.95 degrees, or, so since I have negative, let me get the positive angle. We know that tan of 180 plus theta is tan theta, correct? Tan of 180 plus theta is tan theta, third quadrant. So therefore I can take it as minus 75.95 plus 180. It is 104 point or 104.05 degrees. It is minus 75.95 degree or plus 104.05 degree. So both the answers are correct. So this is the solution for problem number 2. Let me pause this video for a while so that you people can copy it down. Later we will solve problem number 3. Now moving ahead for problem number 3. The problem number 3 states that the damped natural frequency of a system as obtained from a free vibration test is 9.8 cycles per second. So moving ahead for problem number 3, if I list out the data given, the damped natural frequency FD, because it is specified in cycles per second, is 9.8 cycles per second during a forced vibration test with constant exciting force on the same system. The maximum amplitude of vibration is found to be, is given F max as 9.6 cycles per second. Find the damping factor for the system and its natural frequency is the question. Find damping factor and its natural frequency. Let us solve this problem. Find the damping factor zeta and its natural frequency Fn is the question. So now if I move for solution, he has given the damped natural frequency, right? So therefore I can find omega d. Omega d is 2 pi fd. So how much I will get? 2 into pi into 9.8, which is 61.58 or 61.575 radians per second. So similarly I can find omega max. Omega max is 2 pi f max. So it is 2 into pi into 9.6, which is 60.3186 radians per second. So this is the details we have. We know formulas for omega d and omega max. Let us use that. What is the formula for omega max and omega d? So we know that omega max is given by omega n into root of 1 minus 2 zeta square, correct? 1 minus 2 zeta square. Take it as equation 1. Similarly we have omega d as omega n into root of 1 minus zeta square. Take it as equation 2. Now solve these two equations. That is equation 2 by equation 1. Equation 2 divided by equation 1 will yields us omega max by omega d. Omega and get cancels. I'll get the result as root of 1 minus 2 zeta square divided by 1 minus zeta square. Now omega max and omega d are known for us. That is 60.3186 divided by 61.575 whole square. Let us square it on both sides. Is equal to 1 minus 2 zeta square by 1 minus zeta square. So if I solve, I'll get the value of zeta. So what is the value of zeta? 60.3186 divided by 61.575. Square is equal to 1 minus 2 into alpha x square divided by 1 minus alpha x square. Shift solve is equal to, I'll get the value of zeta as 0.197. 0.197. Now I can find the value of Fn. Now we know that natural frequency omega n is equal to, let me find out by using any one of these two, because root of k by m I cannot use because k and m are unknown. I should use either equation 1 or equation 2. So from equation 1, I can write omega n as omega max divided by root of 1 minus 2 zeta square. Omega max is given 60.3186 divided by root of 1 minus 2 into 0.197 square. You get the answer as 62.805 radians per second. Hence Fn is omega n by 2 pi. We'll get the answer as, this is divided by 2 pi, which is 9.996 hertz. So this is the solution for problem number 3. So we discussed the solutions for the question bank, which I have attached to the link given in the description. Kindly click on the link given in the description to get access to the question bank. For that question bank, I am discussing the solution in this lecture series. I have left out problem 2 without erasing it because this is a little bit tricky. Hoping that you are following my lecture series from the beginning of mechanical vibrations, I have solved this problem. This type of problems we have already addressed in free vibration, free damped vibrating systems analysis. I have given the conversion from linear system to torsional systems. Whatever formulas we have discussed for linear systems will hold good for torsional systems also. Only thing is that we should make proper replacements, that are force should be replaced by torque, mass should be replaced by mass moment of inertia, stiffness should be replaced by torsional stiffness, and deflection x should be replaced by angular deflection theta. These are the major replacements you should do. So use the same formulas just by replacing the terminologies from linear system to torsional systems and solve, you will get the answer. So in this lecture we have recollected the formulas which we have discussed so far in forced vibration, and also we have solved 3 numerical problems. In our next lecture, let me take up problems on rotating and reciprocating unbalance. That's all from this lecture. Thank you all.